Yes. So finally we have arrived at the discrete log problem. Right. So what is it? So discrete log problem is the basis of signature schemes used in Bitcoin. Either it is ECDSA or Schnorr. It is based on the hardness of the discrete log problem. You would have heard the term logarithm in your high school probably. So what is the symbol log of AB is equal to x? It means a raised to the power of x is equal to b. If you are working in the continuous plane, real numbers, right? So real numbers, and if I take a to be something like 15 or whatever, and if I plot this curve, just considering only the positive numbers, 15 to the power 0 is 1, okay, it will rise exponentially something like this. Okay, the curve will rise exponentially something like this. It is very predictable, and there are formulas to figure out the right hand side, right? The power, this power term. Even though it is like an approximation algorithm, you cannot find the exact thing because the real numbers is not like integers. Okay, it exists in the continuum. So there are infinite possible numbers. The thing is that there are infinite real numbers between 0 and 1. Think about it. There are infinite fractions. If you take any two small fractions, even in between them, there are like the infinite ones. So you can only do like kind of like approximation, but they are possible, and you can able to get that. But with discrete logs combined with modular arithmetic, think about a decent prime number. Okay, we can take 19. Consider a number 3. Try to plot the graph 3 to the power x. Take a paper and a pencil or whatever. Okay, you can even use your favorite programming language like Python and Matplotlib to plot this graph. Figure out the model, figure out these terms: 3 to the power 1 mod 19, 3 to the power 2 mod 19, and so on to 3 to the power 18 mod 19. Okay, of course we know that 3 to the power 3 to the power 18 mod 19, we know that it's equal to 1 by Fermat's little theorem, right? Because 18 is equal to 19 minus 1, we know that this is equals 1. Like compute up till 3 to the power 17, right? Try to plot the graph. Okay, your graph won't be a smooth graph that we saw in the continuous spectrum. It will be all over the place. Of course not negative numbers, because we are only considering positive integers. Okay, so essentially the idea is that you will find the graph something like this, and even if you take a even bigger prime, in SCP-256K1 we are talking about like 256-bit primes. Okay, such a large primes, it is like very hard to predict where the next point in the graph will be. This essentially is the foundation of the hardness of finding the logarithm in the discrete case. Discrete case means we consider integers as discrete because they are like discrete in the sense like 1, 2, they are very separate. When we talk about real numbers, they are like in the continuum. Okay, so that's why it is like continuous versus discrete. That distinction is there. So in the discrete case, finding the logarithm is very hard. Of course, there are known algorithms to solve these discrete problems. If you are talking about this integer group, when it comes to SCP-256K1, we are going to work with a group in the elliptic curve. That's like completely different. So far, we have studied the modular arithmetic, because even the elliptic curve is based on modular arithmetic. Okay. So when it is based on like modular arithmetic, there are some known like attacks or algorithms to solve the discrete log problem. One particularly interesting case is like the index calculus. Okay, this algorithm, when used, right? So if you choose a prime number to be of 200 digits, this is about like 10 to the power 200. If your prime, the prime number that you choose is less than 10 to the power 200, this algorithm can easily solve using the modern computers. 10 to the power 200 is a big number. For example, how many bits does it take to surpass 10 to the power 200? It takes 666 bits okay, to represent a number of the size of 10 to the power 200. But in SACP256K1, we are only working with 256 bits. How it is secure? Because it is based on elliptic curve. We will like study the algorithm which can potentially solve the elliptic curve discrete log problem also. Right? But that is not as fast as the index calculus. We are not going to discuss the index calculus here, but I'm just giving you the information. So if you want to have a secure, like a cryptographic system based on discrete log problem on the in this integer based group, right, in this integer groups like ZP, P should be in the order of 1024 bits or 2048 bits, which means the signature and the public key that you're going to store in the blockchain is also going to be huge. That is the main reason why elliptic curve cryptography is preferred over a normal, regular, easy to understand like this modular arithmetic groups over primes. Okay. So now all the fundamental maths topics are covered, and from the next chapter we will dive into the elliptic curve cryptography.